So a very good evening to everyone in Malaysia. So to our Astronomical Society of Penang members, and also our astronomy colleagues in Malaysia, Klang Valley, Sabah, all right, and maybe people who are watching from around the world. Okay, good morning, good afternoon, good evening, all right. So this month we are going to talk. It will be on September, all right. APOD, Astronomical Picture of the Day for September. Now let's go to the first day of September. Now, sorry. I have to present what they call present now your entire screen.
Yeah, the share your screen.
Okay. Can you see my AirPod screen?
Can.
Okay. So September 26th, moon phase and the synodic month. Very interesting. This month looks very interesting. Okay. There you are. I'll show you the picture and then I'll show you the description. So this is it. Let's make the thing smaller. Okay. It's by our Marcella Giulia Pace. Right. So she's actually an Italian, what they call, she is not an astrophotographer. She actually photographed atmospheric optics like rainbow phenomena in the Earth's atmosphere. Also, she took for the moon. That means for the moon of the one whole month, all right. In August 2019, last year, she took the moon. For example, you look at this. First, day 17 of the lunar month and day 2 of the lunar month. So day 2 meant basically on the right side. This is actually the second day of the lunar month. KG. Okay. Second day lunar month. So this is the bright part on the right side. But actually on the left side, it should be dark. But she put it in such a way that it put like there's a pair. All right. And then you see the word here, moon phase and the synodic month. The synodic month is when the moon orbits the earth in 1 month, from new moon to full moon to new moon. The whole cycle is called a synodic month, 39.5 days. So you see, second day of the lunar month, which actually the bright part, and 17 day, which is separated by, of course, what they call half a moon, half a lunar month period. So then you have the third day of the lunar month plus day 18. You see, that means the dark part is shrinking and the bright part is expanding. So day 4, bright, day 19, dark. Okay. And then you see, she put a kind of so actually it's actually she put a processes such that you see a dark line. This is not a terminator. This is separate from the 5th day of the lunar month, the bright part and the dark part. All right. And that's how you continue lah. That's day 22, 25, day 23, and day 6, day 24, day 7. And then you see the curvature change. You see, at first it's curved like that. Now it's about straight. Now curved the other way. All right. Day 25 on the left, dark. 8, bright. You see, the bright part is expanding. It's a gibbous moon here. And then day 26, 9 and 9. Day 27 and 10. And finally, you come back to a full circle, which is day 15. Day 15 means the bright part is a full moon. There's no dark part. So this is 15. So very, very nice. So actually, I like to observe this. It's nothing new, the information. Information is nothing new. The way it is presented. All right. So this person here, Marcella Giulia Pace, this Italian person, she know how to do it nicely. Put it like that. All right. So this is our moon phase and the synodic month. All right. Taken by a person who specializes in taking picture of atmospheric optics like rainbows and so on. Okay. So now you go to September 25. All right. Wow. Okay. Hide. It doesn't hide. Never mind. Okay. So you have here by two famous American astrophotographers, Adam Block. All right. Adam Block, of course, is from Tucson, Arizona, and Tim Paquette. Tim Paquette is famous because he has his own observatory in Georgia. All right. For many years now. And his observatory is like observatory grade type. So by Adam Block and Tim Paquette. So basically, you can never take a picture like that. So actually, sorry, it's a Tipu image. not a ray image. They took a picture, maybe one of the either Adam Block or Thomas Puckett took a picture of Andromeda, beautiful picture Andromeda with a satellite galaxy M32 and M110, and also took another picture of the moon and they superimposed. So basically this picture shows, actually, do you know how big is Andromeda galaxy? Andromeda is many times bigger than the full moon. Remember, the moon makes an angle of half a degree or 30 minutes in the sky, you know. So the diameter of Andromeda is much bigger than the moon, right? So imagine you can see the full size of Andromeda galaxy with your naked eye. Then you see that you find that it's much bigger than the moon, right? And then you have the galaxy, the dwarf galaxy M32, and of course here is M110. I've got Andromeda galaxy itself is M31, all right? And of course, all these stars here, they are different colors, are in the foreground. That means it's inside the Milky Way. The Andromeda galaxy is much further, all right? So for example, we know that the diameter of the Milky Way is 100,000 light years. Andromeda is about 2 million light years away. So actually, imagine half the diameter is 50,000 light years. So actually, the Andromeda galaxy is 20 times further than the stars in the Milky Way galaxy. All right, so it's very, very far away, Andromeda galaxy. All right, beautiful. Then you have here, hey, what's this? Apple? No. Green grape? No. Enceladus. Remember, I show you bigger first. One of the moons of Saturn, remember, called Enceladus, the famous moon that has triangle stripes. Remember, the Cassini mission orbit around Saturn many years ago and flew past Enceladus, one of the big moons of Saturn, and saw that water vapor is being evaporating from the surface of Enceladus. But this is taken from Enceladus in infrared, not from the Cassini spacecraft. Cassini spacecraft is already no more, crashed into the atmosphere of Saturn many years ago, taken from the Earth. By who? By our VIMS team. All right. Okay, you go to where VIMS team, where is it? Okay. So this is taken from the Cassini, what you call a mission. It's a telescope that captures infrared light from a special telescope inside Cassini. And of course, this is the University of Arizona in America, University of Nantes in France, and CNRS. CNRS is a national research organization in France. I got my PhD from there also. And then ESA, European Space Agency, is called NASA. So basically, it's a joint venture between NASA, ESA, Americans, and the Europeans, all right, and the French. So you see that here you look at the North Pole of on the left, bottom left is North Pole of this Enceladus, not much. This is the South Pole here. South Pole is interesting. South Pole is where you have the tiger stripe. So when you have red here, doesn't mean it's hot. Remember, the atmosphere of Saturn is very cold, you know, minus 170 degrees Celsius, minus. Here is the dark part is where you have the so-called tiger stripe, where the water, frozen water is breaking out from the surface of the, what do you call this, Enceladus, and evaporating into space. All right. So you can see that this is Enceladus taken in infrared. A lot of information here. All right. This is our Enceladus in infrared. Infrared means what? Wavelength that is longer than the red. Remember, you have the blue, you have the green, yellow, you have the red, and beyond the red, longer wavelength will be infrared. All right, like this. So you see a lot of features of what they call Enceladus in infrared. The next picture. Now, this is very great. Oh, yo. There you are. On the right is the International Space Station. On the left is Mars. Mars, all right. Taken by Tom Glenn. Okay. Now, Tom Glenn is a research scientist and amateur astrophotographer from California. So basically, he took a picture near a place called San Diego. San Diego is the southernmost part of California, just to the south of Los Angeles. So basically, he showed us where he took it. He showed it like, let's say, okay, just northeast of San Diego, like this. Oh no, wait. Okay, so basically he used the Cal Sky software. All right, we go to Cal Sky software now. Okay, so Cal Sky software is a software, the good software for predicting all types of events on the Earth's surface, like the ISS flying across the disk of the sun, the moon, and other events that can be observed on the Earth's surface. So Cal Sky software, and somewhere here is a simulation for California. Okay, so now we see there's a video. All right, this is the video that he took. The video. Okay, I'll make it bigger. Don't close your eyes. Look carefully. This is the whole picture here. From the right, you're going to apply from the right to the left. This is San Diego. The line where it's opposite there. Watch out, watch out. There. Gone already. All right. Another time. There, gone already. All right. So basically, he will now add on until it comes closer. There you are, closer to it. So from the right to the left is a fraction of a second. It's 0.35 millisecond. Very, very fast. And he was able to capture it. And he was able to capture where you have the one of the solar panel of the ISS block off the image from the Mars behind. Mars is very small, you know. So this is very great. Fantastic. All right. So this is our ISS transit of Mars. In this case, for example, Venus of transit over the sun. Venus, the disk of the Venus is much smaller than the sun. But this ISS transit of Mars, ISS is much bigger than Mars. So this is very lucky. Tom Glenn from California. All right. So now this is it. So if you want to predict it, you can. You go to Cal Sky software and you can predict for any location on the Earth, including your house in Malaysia. All right. This the next one is very great. Now you see here, you have actually it's called Equinox in the sky. Luca Vencella is actually sounds like Italian, but she actually is an astrophotographer from Canada. So it's over a city called Edmonton. Remember, Canada is north of USA, and one of the states on the western part of Canada called Alberta. So Edmonton is a big city. You see all the skyscraper, and you can see snow in the ground. All right. So this is Edmonton, looking at the west. So this is looking at the west. That means from Alberta, you look at the west. What do you get? Looking at the west, British Columbia province, and beyond British Columbia is what? The Pacific Ocean. No? So now you see on the right will be the north, on the left is the south, and right and the center below there is the west. And why like that one? So basically, this is the location of the sun. So basically here. So this is one. So right, since this is actually on the 22nd of September, it's actually what? Autumn equinox. So actually, autumn equinox, it should be this one. So this is what? Okay, this is on a sunset. All right. So this sunset meaning that means for that day, 22nd September 2020, a few days ago, the sun was here on the left, top left-hand corner, and it will slowly set. Then go set here. All right. Set here. This is what? Autumn equinox. So for us near the equator in Malaysia, the sun will set exactly in the western horizon, due west. But Penang, Malaysia is about just north of the equator. Imagine you're on the equator in Sumatra. So this is the west. But what he did is this guy, Luca Vancella, very patient. He even did for other days. This is for what? This is summer solstice. June 21st. He did another one for the sun. All right. And of course, that day was 22nd of September, autumnal equinox. And in between also he took. And of course, here's what? Winter solstice. 21st December. So he took a few. Now, this is how many? Not much, you know. 1, 2, 3, 4, 5, 6. 6 only. Some people take even more. So this shows that beautiful sequence of the what they call summer solstice, what they call this spring equinox, and then you have the summer solstice, and then you have winter solstice like this. But also you see because this is Edmonton. Edmonton is very high latitude north. So the sun will set from the top left to the bottom right, tilted. Imagine we take a picture like this in Malaysia. We can, right? But then the sun will not set from top left to right, to the center. The sun will set from top straight down. All right? This is our autumnal equinox, spring equinox. And then summer solstice on the right, winter solstice on the left, down. This shows that you are an equator. What about you are in Australia? Australia will be the reverse. So here in Edmonton is top left to bottom right. But you are in Australia, you see the sunset will be looking at the west. Top from the top right, bottom left. Top right, bottom left. So by looking at how it set in the horizon, in the setting sun, you know by measuring the angle between this series of lines and the horizon, you can measure what is the latitude of the place you took, and whether it's the northern hemisphere or southern hemisphere, or whether you are in the equator, and so on. All right. So this is beautiful. This is our equinox in the sky at different parts of the time of the year. So today, of course, it took its 22nd September, autumnal equinox. Then you have winter solstice, summer solstice, and then later on you have winter solstice. Very nice. All right, from Edmonton, Canada, Alberta. So we can also do this picture in Malaysia, but Malaysia will be straight up and straight up and straight up, straight up. Okay, very nice, very unique. And then this light is called what? They call it the Omega sunrise. All right, Juan Antonio Sandra. Remember, Malaysian cannot pronounce Spanish well. They will say Juan, not Juan. H is like an H. So Juan Antonio Sandra is actually taken from the from Valencia. You know, those who know Spanish football, Valencia football team. Valencia is just next to which city? Barcelona. All right. So Valencia, looking at the east, is a what? From Valencia in Spain, looking at the east, what? Mediterranean Sea. So this is the sun rising from the Mediterranean Sea. Just at the same time, there's a sailboat there. And this is the Omega sunrise. So we always see this. Remember, we see, sometimes we say there is this green flash. When the sun is rising, you see that at the last moment when you rise, there's a green flash at the horizon. But also just before the green flash, you find that, why the shape of the sun is that instead of touching a small point going up, actually it seems to increase, then decrease, then only increase. And so you look, the whole image here look like the Greek letter, last Greek letter, Omega. So they got Omega sunrise. Many people have taken Omega sunrise or Omega sunset. So basically, this inverted image of the sun at the horizon is actually an inverted image of the upper part of the sun here, because of the reflection of the light at the sea, at the surface of the sea, will create this. It's not an illusion; it's a real effect, inverted effect. So it's the Omega effect. All right, Omega sunrise, taken by Juan Antonio Sandra from Valencia, looking at the east. Morning sunrise, very nice. Okay, and this is taken from what? A single exposure on the camera. No tracking, no processing. All right, single picture, very nice. Lucky, yeah. And then this, right? This one may not seem much to many people, but actually, from the scientific point of view, it's very great. What's it? It says breaking distant light. So it's taken from there's a certain telescope called Very Large Telescope, all right, VLT, built by the European Southern Observatory in Chile. And in the Very Large Telescope, you have the famous equipment called BIMOS, BIMOS, and there's a name for this BIMOS. Okay, it's a visible multi-object spectrogram. That means what? Imagine you have a telescope pointing at the star. You can get here, there's a spectrum of the star here. That star or that galaxy, one object. But BIMOS in VLT can have many, many objects in the field of view, and it can take the spectrum. Let's say there are 100 objects in the field of view. It can take the 100 spectra of the object at one go, simultaneously. So this is one galaxy, and a galaxy. So this galaxy. So from we know that from the galaxy that are very far away, you have what? Red shift. galactic redshift. So the galaxies that are at a certain distance and further, their wavelength is always what they call extended to the longer wavelength redshift. So here you see so many redshift of so many galaxies. So if you do that, you'll find that maybe this basically what is this? The spectrum here has many of the what they call the dark lines here. The dark lines are the absorption line of the galaxies, and the absorption lines are the absorption line of not the galaxy. The galaxy is made of many stars. The absorption lines are the absorption lines of the stars that make up the galaxy. All right. So from here you find out. Let's say there's a certain line, hydrogen singly ionized line. So from the redshift of the singly ionized line for the ion, you know what is the redshift for that galaxy. And below it, another galaxy. So you can get the redshift for all these galaxies at one go. And this is great. So can you imagine? Many amateur astronomers, they are doing what they call taking redshift of the galaxy. They put a spectrograph on the telescope, but they take the spectrum of the galaxy or the star one by one by one. But BMOS in DLT take all at one go, and most likely they will analyze it by computer. Can you imagine? So this is our breaking distance light into the redshift of all the galaxies very far away. All right, with the multi-object spectrograph in very large telescope. All right, and of course, if you want to look at a very large telescope, we must always talk about it. It's very great, It's my dream to visit there. You are. Wow, wow, wow. Okay, go and look at that. It's a series of 4 big telescopes. All right, and they have this single mirror telescope. Each single mirror is 8.2 meter diameter. Ritchie-Chrétien optic. So you have 4 telescopes, each of 8.2 meter diameter, and you also have some smaller telescopes, so that they can do what's called long baseline optical interferometry. But these 4 telescopes, each single telescope 8.2 meter, and they have names, So it's taken this telescope that take the spectrum just now. They have named very nice name. So the names are, you see here, like I repeat, Yepun on the left is a native language, the Mapuche. Previously you have the native in Chile called the Mapuche Indian. They use the word Nepun. So Yepun means serious for them. And then you have this one on this in the center, Antu. Antu means the sun. And then you have Quayen. The Mapuche means the moon. And on the right is Maripal. Maripal means Southern Cross. So these are the very large telescope in Chile. We took this picture. All right, distant light, great, So I'm very sure you cannot take it instantly because the galaxies, some of them are not so bright. They may take many hours to collect the light and to obtain the spectra of these galaxies. All right, remember, one object is one spectrum law, 2 objects is 2 spectra law, many objects is many spectra law. Okay, that's it. Now you go look at this, September 19. Wow, nice. So I'll give you some information first, then I enlarge again. Okay. Now this is Ronald Davison. Interesting, He's an electrical engineer from New York, New York, but for hobby is astrophotography. So basically this, he want to show you, most of us are familiar with Orion, isn't it? Blante, okay, Lia Huchuo. So you find that if you look at the plane, this is what we see, all right? Yeah, Betelgeuse, Bellatrix, Anita, Anila, Mintaka, and below is Rigel and Saif. But now he plot not like that. He plot also to towards the top left is the distance from the Earth. So if this is the Earth, all right, can you hear and see me clearly, Xinzhong?
Can.
Okay. So now, so as you go further, actually, what to us we see Betelgeuse very bright. Oh, there, very near. It's about 498 light years only. The furthest one is right in the center of the 3 stars, Anilam. Ooh. Anilam is 1,976 light years away. And because Anilam is so far away, its apparent magnitude is 1.7, but its absolute magnitude, which shows how actually bright it is, absolute magnitude is Anilam minus 7.2. Very bright, which makes it many times brighter than Venus. When Venus is what they call at the brightest. All right. So imagine Anilam is much closer. Wow, it can be even brighter than Venus. Right. So this Anilam is 1,900 over light years away, and then the one that is here is not bad. You know, the M42 Great Orion Nebula is 1,344 light years away, very far away. You know. All right. And then after that you have Rigel quite far away. All right. So Rigel is 863 light years away, and not bad. Absolute magnitude is minus 6.9, very bright. All right, we know that Rigel is very bright, but because it's very far, much further than Betelgeuse. If Rigel is as close to the Earth as Betelgeuse, then Rigel will be much brighter than Betelgeuse. All right, and then you have the later on, you have the closer to the Earth, Anita, Mintaka, Sai, Betelgeuse, and the closest is Bellatrix. All right, now we know that star names are mainly derived from Arabic, like Anita, Anila, Mintaka, Rigel, Betelgeuse. But Bellatrix is derived from Greek, not from Arabic, from Greek. All right. So it's very close, 252 light years away. So I really like this image. All right. This is one. Orion in depth. What is the distance of the various objects in Orion from the Earth? All right. Very nice. Next. Okay, we look here. I make it bigger so that you can see. Okay. ARP up, peculiar galaxy in Aries, taken by Bernard Miller. Okay. Okay. So basically, Bernard Miller is from the state of Missouri, in Central America. He's actually he works in a software, no, CAD, computer AD design company. So it's an Aries. Now remember, this peculiar object, all right, is in the catalog of our American astronomer called Hudson Up. Then many years ago, there's an American professor astronomer called Hudson Up. He collected in his own catalog of peculiar galaxies. And now we know that the peculiar galaxy like this up 78 is what? There's some kind of, this is a galaxy here, but it's suffering a kind of a galactic tidal interaction, right? Tidal doesn't mean the water tides, no. The star got water, no. That means the somewhere nearby, there are other nearby galaxy. The gravity of this nearby galaxy will pull the stars, will stretch out the stars, will churi the stars, will steal the stars from this main galaxy. And it's like twisted out. And you see a beautiful spiral arm here. And you see the twisted arm, the tidal tails pulling out. All right. So this is our peculiar galaxy in Aries by Bernard Miller. All right. So really beautiful. So this is our 100,000 light years across. Right. In Aries, the ram. Remember, in Latin, the ram means a kind of a goat, a mountain goat that can walk on the steep part of the mountain very well. Okay. Now we will go bigger so you can see. So I give you everyone have some good news. September 17. There you are, September 17. Wait. Okay. Solar cycle number 25 has begun. All right. By NASA and SDO. So what is SDO? Remember, SDO is our Solar Dynamics Observatory, set up by NASA in 2010, many years ago. I remember about 9 or 8 years ago, two of the NASA scientists came to Penang, you know, Dr. Jaya Bajpai and a colleague. So Dr. Jaya told me she's one of the scientists working on SDO, Solar Dynamics Observatory. So basically this is, on the right, you find that, okay. Now, we'll go and look at the bigger picture first. Yeah. So right now, they claim here that December 2019, the sun has activity has reached its minimum on the right. You see on the right part, the sun is at the minimum. Now, don't think that the sun is in chocolate color. No. Solar Dynamics Observatory observe the sun in short wavelength, shorter even than UV light. So all these are actually, you look at with your naked eye, you cannot see. That's shorter than UV light. For example, in the extra ultraviolet light, even shorter. So you see, December 19, the sun was very quiet, but this was when the sun on the cycle, this is cycle number 25, it started when December 19. But this was the maximum of December, maximum of cycle 24. You see, very active. But this is December 2019, very weak. So what are we going to do? Well, I say good news. The sun will get, as time goes by, now it's what, September 2020. Nearly 1 year up past the minimum. All right. So it will be getting more and more active. So starting from December 2019, the solar activity, the number of sunspots will get more and more. So we hope to see more of the sunspot coming and also more of the solar prominence. All right, and so on. So this is it. So this is taken by SGO. And I remember Dr. Jaya Vajpayee, I asked her quite a lot of questions. She told me that actually the NASA scientists have discovered something very interesting about the sun. Because previously, the astronomers, they considered the sun to be a fixed star. The brightness of the sun do not change much. Stable star. But the data from the solar dynamics observatory proves that the sun is actually a variable star. The output of the energy from the sun goes up and come down, goes up, come down, but not by much. It's about, she told me about 30 parts per million, but can be measured by SDO. So now the sun is no more considered to be a fixed star, stable star, but a variable star. All right. So on the right is cycle, what they call the minimum of cycle 24. All right, very dim, and the maximum of cycle 24. All right. Maximum. And now we are in the beginning of cycle 25. Okay. Now, of course, they start monitoring the solar cycle since the 18th century, since 1755. They have been monitoring the solar cycle. All right. So this is the cycle 25 has begun. So we hope to have more and more sunspot, more and more activity in future. Okay. So now let's look at this. September 16, gravel ejected from asteroid Bennu. Oh, very interesting. Okay. Interesting, eh? Okay. So of course it's taken from OSIRIS-REx. It's a robotic spacecraft launched by America some years ago that orbited what they call this an asteroid called Bennu. All right. And of course, by University of Arizona, and then you have NASA here, and Goddard Space Flight Center, GSFC, and of course Lockheed Martin is the one that built the spacecraft. Of course, Lockheed Martin is also a defense company making a lot of fighter jets and so on. They also make this spacecraft. So it was launched some years ago, and interestingly, when the OSIRIS-REx passed close to this what they call Bennu, asteroid Bennu, they found that, this is not a star, no. This is a pieces of rock flying out. So they said that it could be that there's water trapped, frozen below the surface of Bennu, evaporated and ejected the gravel. Gravel means large lumps of rock flying to space. So they're thinking, why can throw out all these rocks from the surface of Bennu, right? And then what they call, very interesting. And remember, we are waiting for next month. All right. So next month, this Bennu in October 2020, next month, the OSIRIS-REx going to land a lander, robotic lander on Bennu, take some of the sample from Bennu and come back to the Earth in a few years' time. All right. So another one we are waiting for a long time is what? Our Hayabusa 2. Remember Hayabusa 2? The Japanese sent the second spacecraft, robotic spacecraft, to land on an asteroid called Ryugu. All right, Ryugu asteroid, and took a sample of from the Ryugu asteroid on the way back to the Earth. And when it's going to land on the Earth again next month, October 2020, it will land somewhere in South Australia, north of Adelaide, in the Woomera Test Range. The Woomera Test Range is a isolated, deserted area where many years ago the British tested their atomic bomb there. All right. So the Japanese, what you call Hayabusa 2 spacecraft got a sample from this asteroid Ryugu will land on the Earth. Okay, previously, many years ago, Japan sent the first successful sample return mission from asteroid. What? Hayabusa 1 spacecraft took a sample from asteroid Itokawa and brought it back to the Earth. All right. So now we are waiting for this Osiris-Rex to land on this asteroid Bennu, take a sample of it next month, and fly back to the Earth in the previous time. All right. We hope it will be successful. So why, if we can take the sample from Bennu back to Earth, so we will see or learn a lot about this asteroid. But very unlikely they will find life. They will find amoeba, they will find ikan bilis. But at least they will get a lot of information of the asteroid, because asteroids are considered as the primordial material, the original material that failed to form a planet. If the asteroid all collected together in the asteroid belt, can form a planet, but it failed to form a planet. So that means the asteroid material is about the original part of the material that formed the solar system, not being processed at all. So the material from this asteroid Bennu will be very, very useful for the scientists. All right. So we continue. This is a big news. 10 years ago, Venus. All right. Okay, Venus here is taken by our what do you call this Japanese exploration space exploration agency JAXA, and this is taken by the Japanese have sent in a spacecraft 10 years ago, 2010, Akatsu, and processed by one amateur astronomer. So sorry, not Akatsu, Akatsuki. So Akatsuki was a spacecraft launched by Japan many years ago, supposed to orbit the Venus in 2010, but it was sent into the wrong orbit. It missed the Venus, and it was like a lone ranger traveling around the solar system. All right, this Venus around the solar system. But later on, the Japanese rocket engineers, where is the Japanese Cape Kennedy? Not in Florida, no. Tanegashima Island in southern Japan near Kyushu. All right. So then the rocket engineers in JAXA was able to change the trajectory of Akatsuki. So later on, Akatsuki successfully entered into orbit around Venus. And the data from Venus is that they found that this Venus got this not on the top cloud, not on the lower cloud, in the middle deck cloud was phosphine. So what is phosphine? I'll show you what's phosphine. It's very exciting. So when this came out, wow, everyone in the world interested in astronomy went gaga. All right, I'll show you. So we start phosphine molecule. There you are. There you are. So basically, you can see here on the right here, the center orange is of course phosphorus. The white one, the three white one is a hydrogen molecule. So what do you call connected between the phosphorus atom and the hydrogen atom is a covalent bond. So you have three covalent bond binding the three hydrogen atom to one phosphorus atom. So this is a phosphine molecule. So they detected phosphine where? In the middle layers of the clouds of Venus. And this really surprised astronomers, because from what we have studied on the Earth, that the molecule phosphine is usually produced by living organism, like bacteria or whatever. Living organism will combine phosphorus in the organism and hydrogen to give phosphine molecule. Whereas natural processes, lightning, whatever reaction of the rock, all the geological processes in the rock cannot produce phosphine. Only biological processes, living creatures can produce phosphine. That's what makes it interesting. But anyway, you may say, how did they detect it? Of course, they detect it by what they call it was actually the main person who discovered was a professor from Cardiff University, right? Okay, Professor Jane Greaves from Cardiff University, she and the team went to this telescope in Hawaii, James Clark Maxwell telescope, and they also they used the ALMA telescope. So basically, these telescopes are what? Sub-millimeter wave radio astronomy. Radio astronomy at very short radio wavelength. For example, they detected phosphine using infrared light. All right, the light is about 1 millimeter wave. So I'll show you here now, if you don't mind, the spectral lines of phosphine molecule, how they detected it. All right, spectral lines of phosphine. Very well on the right here. Look at the right here. Whoa, so much. I repeat. The vertical axis, of course, how much is the absorption? Remember, the phosphine, the spectral line is the absorption line, because they will absorb the light from the surface of the Venus, and as they pass through the clouds of Venus, they absorb. So basically, many you see. So basically, the spectral lines of phosphine in the infrared region is tens of thousands of lines. So basically, it's what? So look carefully. Now, when you have a phosphine molecule, phosphorus and 4 hydrogen, it's not that these 4 atoms will remain like that. No, they're always in constant motion. For example, between this phosphorus atom and this hydrogen atom, they can vibrate. That means the covalent bond can become longer and shorter and vibrate at very high frequency and vibrate. And usually the vibration frequency is what? Infrared. So these 3 bonds will vibrate and they will absorb the infrared wavelength from below the in the surface of Venus, pass through, they absorb. So you can, when you measure the spectral line, you are still measuring the vibrational frequency. And because this vibration frequency is connected to one phosphorus atom and hydrogen atom, what? Quantum mechanics, what? So it's such a vibrational quantum mechanics. And then because of it's called quantum mechanics, the lines are all discrete. Actually, here you look like they are joined together. No, between one line here, absorption line, and next line, there's a certain gap where there's no absorption. And that gap is forbidden. But where there is a line here, it's allowed. So you have tens of thousands of infrared absorption line. All right. So is that the only motion for the phosphine molecule? No, the molecule can rotate. Now, vibration means the hydrogen atom and the phosphorus atom the distance here can vibrate, but the whole molecule can rotate. But the rotational energy, again using quantum mechanics, is not so energetic. So rotational energy will absorb and give off what? Long radio wave. So when they look at let's say the Great Orion Nebula, they observe that there are some of the radio wave coming from the nebula. Oh, maybe you have this phosphine molecule in the nebula that is rotating. All right. So I repeat, rotation means not very energetic process. Long wavelength, radio wave. Then vibration, more energy. All right. Vibration, more energy. Vibration, maybe I think maybe milli electron volt. All right, will give off infrared. Now, what about inside the phosphorus atom, hydrogen? The electrons in the hydrogen atom or the phosphorus atom can also have transition, and this will give a what? Visible light. All right, visible light is what? A few electron volt. So by looking at the energy given off, we know exactly what's happening in the molecule. So what about inside the phosphorus atom? Inside the hydrogen atom, say the phosphorus atom, there are many neutrons and protons inside. So when the proton neutron interact, they give off more energy, mega electron volt. So when you see anything like that, what will it give off? Gamma ray, strong X-ray, very powerful X-ray. So the more powerful the process, the shorter the wavelength. Of course, the most energetic is something happens in the nucleus, gamma ray, X-ray. But then beyond that, you have the electron shell can give off light, visible light. And then the vibrational, what I call energy band, quantum mechanics will give off what? Infrared. All right. And then you have a rotation of molecule will give off what? Radio wave. So that's how they know what's happening in the molecular clouds or in the center of the stars. All right. So this is how they detected phosphine, all right, in the atmosphere of Venus. Big discovery, because now you can see there are now many professional astronomers are working now over time. They say that the future mission to Venus is to map out, to find out more of this phosphine molecule, right? And they hope that more and more people will be interested to find life or signs of life in Venus now, right? So Venus will be the place to go to look for life in future, because confirmed they have phosphine, all right? Detected by the Japanese spacecraft called Akatsuki by JAXA. JAXA is Japanese Space Exploration Agency. JAXA is the Japanese NASA, all right? So we go again. The next one is September 14. Go for big object first. Okay. Wow. Corn moon rising. Because corn moon is just like the Masali, the Europeans, American, they always have harvest moon, corn moon. This is called corn moon. All right. And then this one is, okay. So this is taken by Zarcos Palma. I think he's a Portuguese astrophotographer. So he took a picture of this corn moon rising. All right. Rising. All right. And this is captured from Portugal. All right. Portugal. But the mountain in front here where it's rising is in Spain. So it's at the Portuguese Spanish border. And you can see the moon rising. And again, you know that this picture is not Tipu is correct. Because why? It goes from the lower left to the upper right, just like the what they call the solstice picture over Edmonton in Alberta in Canada. So this lower right to the upper, no, lower left to the upper right, rising moon. All right. But if you are in Australia, it will be different. The moon will rise from the lower right to the upper left in Australia. But this is in the northern hemisphere in Portugal. All right. Okay. This is the corn moon rising. Very nice. So he was in the correct position at the correct time. Zarcos Palma, Portuguese astrophotographer. He took this moon rising. Very nice. And this is nice. November 13. Wow. Ooh. Small picture first. Look at how beautiful it is. All right. Actually, this one Hubble have taken for many years. This again, of course, by Hubble legacy. So remember, many of the pictures by Hubble is actually co-owned by ESA. So NASA owned by NASA and also ESA. ESA is of course European Space Agency. NASA means American Space Agency, and processed by one NASA scientist, Judy Smith. So she seems to be an expert in image processing. So she processed it. So it's M2-9, wings of a butterfly nebula. All right, wings of a butterfly nebula, September 13. All right, and then this one is where was it? Oh, yeah, it's taken of course from what they call. So this is an example of it's a bipolar appearance. So whenever you have a bipolar appearance, you straight away you say inside got binary star. So right in the center, there are two stars orbiting around each other, and one of them may die earlier, and before it dies, it will pop out, it give out a lot of gas and dust and material, and because of the two stars orbiting each other, we create two lobes, 2 ears sticking out. So bipolar appearance. So anything bipolar means there's a binary star inside there. All right. So this star, this is in M what they call 29. All right. Now which constellation? Never mind. So this is in taken by NASA. The next one. Wow. The next one is, look here, 1,000 meteors. All right. This is taken by Greg Priestley, an amateur astrophotographer from New South Wales in Australia. So basically, this is the view here. I will now turn on the video. Look at the meteor. This is not a specific meteor shower, Perseid or Gemini. No, this is random, taken throughout the whole night. All right. So now I'll make it bigger and then play the video. Okay. Play the video. There you are. 1,000 meteors on that night. Some fireballs can be seen. See from all directions. Fireball. Milky Way. And of course, the trees are shaking because of the wind blowing. Fireball on the left. Very nice. Greg Priestley from New South Wales, Australia. Yeah, you see Pleiades star cluster. Orion there. Wow, another fireball. So nice. So that time he took 1,000 meteors, you know. Now the reason why it's like that, Australia, very many places in Australia are very, very dark. So lucky. See, you don't see a single cloud in the video, all right? So by Greg Priestley, 1,000 meteors in New South Wales, Australia. Then now September 11. Okay. So this is the dark side of the moon, and there's Mars, all right? And then you have reappearance of Mars by our David Duarte and Romualdo Caldas from Brazil, 2 amateur astronomers from Brazil. So remember, Brazil is interesting because they were able to see Mars, lunar occultation of Mars a few times this year, no? So this is the number 4, the 4th time. This year there are 5 lunar occultation of Mars. This is the 4th time they saw. Previously, I think last month, in August, we saw the Mars entering the bright part of the moon, all right, called the ingress. This is the egress. Egress means the Mars is coming out from the moon, all right? So there you are. So this is, they took, they were able to get this thing from Mars, all right? So now let's look at let's say for, okay, so let's say in this year, how many lunar occultations on Mars are there? You see, we click onto the website, our lunar occultation website. A bit slow. Okay, Sim cannot get. Never mind. We go to the next picture, but I'll try to open this window. If it comes up, I'll show you again. Okay, so this is the Mars coming out from the moon. All right, taken from Brazil. This is the 4th time this year. All right, so the South Americans are very lucky for this year. Oh, it's not working. Never mind. So we go to the next date, September 10. Okay, Jupiter, the moons of Jupiter and the Great Red Spot, and this is called Jupiter's swimming storm. All right. So Jupiter's swimming storm, I will enlarge it for you first. You can see the swimming storm is not the Great Red Spot. Great Red Spot have been blowing for a few hundred years, but this one here, you see, so there's a storm brewing. So basically, this is what. So this Andy Casely is the amateur astrophotographer again from Australia, and he specializes in what? Planet images. So Mr. Andy Casely from Australia is a planetary imager. So images the Jupiter, and you can see the details of Jupiter and also this storm brewing, just this thing here. So there are people in the world that focus mainly on Jupiter. Of course, the famous one is, of course, our Mr. Christopher Goh from Cebu City in Philippines. So our Christopher Goh, not a very big telescope. He put a telescope in his house in Cebu City, not so much light pollution. And he imaged Jupiter whenever the weather is good. He has so much data that nobody got the data like him on the Earth. that the NASA consider Mr. Christopher Go as the NASA's Jupiter ambassador for Jupiter. Christopher Go from Philippines, but this is Andy Casely from from Australia. All right, so you can see this storm coming out, which previously did not occur. All right, a storm coming up in Jupiter. Of course, you can see the great red spot. All right, the next one, September the 9th. Okay, Pleiades, Seven Sisters star cluster. We have seen that before, but never mind. Just look at it. There you are, Pleiades, beautiful Pleiades. Okay, by Senor Raúl Villaverde Fraile. Okay, Mr. Raúl, of course, is a Spanish astrophotographer, but this is quite a big picture. I will make it smaller so you can see the whole picture. So beautiful. Wow. Remember, for most people say, tujuh adik-beradik, Chisenway, seven sisters. But no, with a powerful, good telescope and with a camera, there are actually 1,000 sisters. 1,000 sisters in the Pleiades star clusters. All right. And they are all very what? Young stars. Why? You look, each of the stars here is emitting a lot of those nebulosity. They're ejected out. So it's a stellar wind. See, our sun gives off a solar wind. The solar wind of the sun is the electrons and protons coming out. All right, very fast. The solar wind is shooting up from the sun at about 500 kilometers per second. But the number of electrons and protons coming out is not so much. Whereas the stellar wind from here is tremendous. I don't know, you compare to our sun solar wind, the stellar wind around here will be like a typhoon, like a big typhoon, like a hurricane. So very dangerous. The stellar wind is very powerful there. So these are the young stars, all right? And because of it's very energetic, so the light is blue color. And what I find is very interesting. Yeah, look here. Hey, I've never seen it before. In the Pleiades star cluster, you can see some dark areas. The dark areas here does not mean that there are no material here. So there's a hole in the space. No, the dark area means that there are a lot of material there. What is the matter? Dust, absorbing material. So here you have material giving off light. Here you have dust and material blocking the light from behind. So you can see a lot of those called dark areas, all right? Absorption nebula in Pleiades star cluster region, right? So this Pleiades star cluster in Taurus the Bull, all right? Very nice. By our Raúl Villaverde in Spain, taken from Spain. Next one. September the 8th. This is interesting. Now this one, some people see already, kepala pening, tauhin. What is this? So it needs a kind of explanation. Very interesting. Now remember, ladies and gentlemen, boys and girls, 2016 was a big year. Why? They have discovered using the LIGO gravitational wave observatory in America. Two of this observatory found the first detection of two black hole collide and give off gravitational wave. So they have discovered a lot of gravitational wave event. But this one is from GW190521. So it's a collision of two black holes. But this black hole, the earlier one in 2013 was two black holes about a few solar mass collide together. But this no, it's two black holes, one black hole of 66 solar mass and a second black hole of 85 solar mass. They collide. So this is not the real picture. This is what a simulation now. So this is one of the black hole, 66 solar mass, and it shows the spin axis because black hole must have black hole properties must have a spin, must have electric charge, must have a mass, So they have a spin, but it's spin like that, they spin like that, and then you see why is all these lines all distorted because the gravity around black hole is very, very strong. So the not time, not space, space-time. Space-time is tremendously distorted around here. So basically, I would say that this picture is generated by using they use the word numerical relativity. Now, you cannot use your computer, your desktop, or your handphone to simulate, because the amount of calculation needed to calculate this type of space-time next to these two black holes tremendous. So maybe you need supercomputer. All right. So numerical relativity, the program using the Einstein field equation, were able to simulate the condition of the space-time of these two black holes just before they collide. You see here, like there are a lot of bending, a lot. So basically, this one, this is not two waves, no. This is that the space-time is more distorted, here less distorted, more distorted. So if they collide, these two black holes, the green one go to the right, the left one go to the left, collide. So what will happen is, at the moment of collision, it will give what? A burst of gravitational wave. Not gravitational wave, a burst. And this wave will spread out all over the universe at the speed of light. And it was detected by our this Virgo. I'll show you what it is. By our Raúl Rubio. He's a scientist in Spain working in the Virgo Valencia group in the Virgo telescope. So Virgo telescope, you know, is another gravitational wave observatory where in Italy. So the two famous ones are the LIGO 1 and 2 in America. But they also have Virgo in Italy. They also have gravitational wave observatory already working in Germany. These three countries. But in future, they're going. No, there's one already built already. I think it's working already. In Japan, they have a gravitational wave observatory. And which country is joining the gravitational wave race? India. India also building gravitational wave observatory. All right. So this is produced by Raúl Rubio using a computer simulation of two very big supermassive, not very big black hole colliding. Remember, 66 solar mass, 85 solar mass is called intermediate mass black hole. Remember, black holes they have discovered many years ago, stellar black hole from a few solar mass to maybe 10 solar mass, 15 solar mass. And then you have also supermassive black hole, the one in the center of Milky Way, 4 million solar mass. The one in M87, 6 billion solar mass. But they are now beginning to find black holes that are in between stellar solar mass and supermassive. So this is a collision of two intermediate sized black holes, 66 solar mass, 85 collide, and they give a burst of gravitational wave spreading all over the universe, and was detected in Italy. Right? Very nice. All right. So we are going to follow more and more. So they are going to have more and more. So they said that in future there will be so many gravitational wave observatories in the world that they will say that they will be able to detect every day, not once a year, no, every day, many gravitational wave of events. We hope that will come. Yeah. So now we have also September 7th. Walala, so nice. Okay, so this is the Milky Way over St. Michael's Mount by Simon R. Hudson. Now, Simon R. Hudson is actually a British amateur astronomer. I think he also works for the BBC, right? So now I make the picture smaller. Smaller some more. St. Michael's Mount. Actually, St. Michael's Mount is say here. Actually, this is an island in the sea near Cornwall. You remember Cornwall? It's a Negril estate in the southwestern part of England. All right, next to the ocean and next to the English Channel. And during the low tide, you can see the road goes to the island. But during the high tide, it's all covered by water, and this become a real island. This is St. Michael's Mount. Now, don't confuse this by another one, the more famous one, Mont Saint Michel. The Mont Saint Michel is a similar place, of course, world famous. This is not so famous. This is St. Michael's Mount in England. The other one, Mont Saint Michel, is also a castle and a town on the island. Low tide can see the road, high tide block. But that one, Mont Saint Michel is in Normandy in France, also famous. But this is not so famous place, but also very nice. So our Simon R. Hudson, astrophotographer from UK, works with BBC also, took a picture of Milky Way setting over St. Michael's Mount. So nice. And on the right, you see a meteor trail. And on the left, you see Jupiter. And of course, many stars. And you see the Milky Way. Very nice. All right. So this is our Milky Way over St. Michael's Mount in England. So the next one will be September the 6th. This September the 6th. Crab M1, Crab Nebula from Hubble. Actually, ladies and gentlemen, boys and girls, this is an old picture. This taken by Hubble many years ago, but from time to time, I think the two APOD people, editor, they recycle some of the picture. But this is a very important picture. I think it's worth recycling. Of course, taken by Hubble, okay, owned by NASA and SR. And then this is, of course, in the M1, let's see object 1, in Taurus the Bull, and it exploded many years ago. It exploded here, it says, in 1050 AD, nearly 1,000 years ago, and was recorded by the ancient Chinese astronomer. So the Masale, when they see any type of event, a new event occurring in space, a new star appeared or new supernova, they go and check the Chinese astronomy record, Japanese astronomy record, Korean astronomy record, and other ancient civilization they will check. So in the Chinese astronomy record, they have recorded a lot. So this one in the year July of 1054 AD, suddenly the Chinese say, hey, from nowhere, a bright star appeared in the sky. And when it was brightest, it was magnitude -7, you know. The supernova explosion in M1 was magnitude -7, many times brighter than Venus. And it was seen in the daytime for nearly 3 weeks. Can be seen in the daytime for 3 weeks, in China, 1054 AD. And then later on, when the supernova exploded, expand, become dim again, then disappeared. And now it disappeared from naked eye visibility. But when it's the brightest, it could be seen in daylight. At night, at the time, it was four times brighter than Venus. All right. And we know that during the supernova explosion exploded, from the supernova astrophysics, they know that the remaining part, it can form either a neutron star or a pulsar, which is a fast rotating neutron star, or a black hole. But in this case, they form actually a pulsar. A pulsar that is spinning on its axis at 30 times per second. So in the center of this M1, you have a millisecond pulsar. That means every millisecond, there is a pulse. Imagine instead of, so this millisecond pulsar in M1 is not only giving off radio waves, Some of the pulsar give you all radio wave, but this one given in all wavelength. Gamma ray, X-ray, visible light, radio wave, all. So imagine, instead of seeing the light by sight, we listen to the pulse. So if you listen to the pulse, what is the pulse converted to sound given off by the pulsar will be what? Ding 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 ding. Every second, 30 ting. So that means there's a millisecond pulsar. Why is it ting 30 times? Is because the axis is spinning. And we are lucky that the axis of spinning from time to time will point towards the Earth. It can ting, 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 and we don't hear ting, ting, ting. Because the axis, when it spins, it will not point at the Earth. So we don't hear. But this one is lucky, it points at the Earth. All right. And we also know that, do you know, ladies and gentlemen, this is a fact which I found out many years ago as a student in US. I was very amazed, Even today, amazed. At the moment of a supernova explosion, what is the maximum energy output of the supernova? Is it visible light? No. X-ray? No. Is it electron? No. At the moment of explosion of the supernova, 99% of the energy that is given up is in the form of neutrinos. The particles that are very hard to detect. So at the moment of supernova explosion, neutrinos are given off. So whenever the scientists, they have actually a big neutrino detector in the mountain on the Earth, in Japan, America, Canada. So they have what is the neutrino detector for? To detect supernova. When the supernova explodes, the burst of neutrino, 99% of the energy given off at the moment of explosion of the supernova is in the form of neutrino. All right. So we go back. September 5. All right. Interesting. There's a moon. a rocket. So Katie Darby here, she's actually what I call a photographer, not astrophotographer. So actually she's lucky. So she stays in Florida, where you have the Cape Kennedy, Cape Canaveral Airport Station. So this is the Falcon 9 booster stage landing. Remember the Falcon 9 spacecraft by SpaceX, or Falcon 9 Heavy, also by SpaceX. The main rocket got 4 at the bottom. The first stage got 4 booster rocket. This is one of the booster rocket. So we launch it on top. So the main part of the rocket will boost the Falcon 9 payload into space. But the 4 booster will land back onto the solid ground in Cape Kennedy. So this is the landing part of one of the booster. All right. So our Miss Katie Darby took a picture. So normally if you go to Katie's website, interesting. You know what's the most of the pictures she have? Her pet dog, anjing. A lot of pictures of her dog. She liked the dog. But at that time, she was lucky. Maybe she was near to the Cape Kennedy Airport Station when they launched the SpaceX, and she waited for the first stage booster to land, and she was able to take the picture of the SpaceX first booster rocket and also the moon at the same time. So lucky. Okay, so now we have September 4th. Wow, very nice. The Wizard Nebula. Another astrophotographer, Andrew Klinger from Texas, USA. Now remember, we have also a kind of never mind. So the Wizard Nebula means there you are. This look like a face there, the wizard. All right. But that when I saw this, I already realized that hey, there's something interesting. For example, we have another nebula called the Witch Head Nebula. All right, the Witch Head Nebula. We start again. Okay. Okay, the Witch Head Nebula looks like that. On the right side, Oh, Nebula Bomo. But this is a face of a woman, a witch. Right? So this is actually a reflection nebula. And on the right, out of the field of view, on the right is our star Rigel in Orion. So it gives a lot of light from Orion, from Rigel, and it reflected from this nebulosity. So this is a Witch Head Nebula in Orion, and this is what they call Witch Head Nebula. But this is called what? A Wizard Nebula. A Wizard Nebula means a Bomo who's a male. So this is a Wizard Nebula also, all right, taken by Andrew Klinger, our astrophotographer from Texas in America. Very nice. We go to September 3. Wow. What's this? So something bright and purple color and bright, and a bit of Milky Way. And this is a hill here in the background. And of course, this is by NASA and ESA. All right. So basically, this is not a real picture. This is actually a digital simulation. All right. So basically, this is, sorry, I call it the Tibu image, not a real one. So actually, the scientists were able to detect around the Andromeda galaxy here, this Andromeda galaxy. All right. And far away from Andromeda, there's a lot of hot gas. Hot gas meaning what? Hydrogen gas lah. In the universe, most of the material gas is hydrogen gas. So when you say hot, hot doesn't mean wow 100 degrees Celsius. No. For astronomers, hot may mean say minus 100 degrees Celsius, because in the universe everything is very cold. I repeat, if you ask me, what is the average temperature of the space between the star, between the galaxy? So I would say the average temperature is actually the temperature of the cosmic microwave background lah. So what is the cosmic microwave background? Remember, the Big Bang occurred, what they call 13.8 billion years ago, exploded. At the moment of explosion, the temperature of the Big Bang was trillions and trillions of degrees Celsius. And when the expansion occurred, more and more, expand more and more, the temperature drop. So now at the temperature the average temperature of the universe, the space between the star, the space between the galaxy is actually the echo of the Big Bang, and in the microwave region. And the microwave is given by the object when it's about close to 3 degrees Celsius. No, sorry, 3 degrees Kelvin. All right. 3 degrees Kelvin means what? Minus 270 degrees Celsius. So that would mean that the average temperature of the space in between the star and the galaxy in the whole universe is about minus 300 degrees, no, minus 270 degrees Celsius. That is the average temperature. So that means that very cold, minus 270. But that means the temperature here could be say, let's say 100 degrees Kelvin. 100 degrees Kelvin could be say minus 200 degrees Celsius. But because it's warmer than the average temperature of the universe, right? Which is minus 270 degrees Celsius, but this is 200 degrees Celsius, minus 200 degrees Celsius. So it's still warmer than the average temperature of the space. So they found that there's a hot gas. So actually, they took a picture of this Andromeda and they just digitally, put a graphic, process it to look like purple here. They artificially put it in, and they put it artificially a landscape view. So this is not a real picture, but just to show that next time you look at Andromeda Galaxy, you know that just now we saw one picture, Andromeda Galaxy is much bigger than the moon, So this Andromeda Galaxy, the moon is just a dot in the center, So this is the size of Andromeda Galaxy, but around it, there's a kind of halo, all right? A sphere of hot hydrogen gas all around it for many, maybe from right across it, I don't know, look at here, the Andromeda Galaxy, say 100,000 light years, this could be, say, 500,000 light years, all right? So it's a hot halo of gas, hydrogen gas around Andromeda, all right? That's the meaning of it. Next one is September the 3rd. No, September the 2nd. Oh, okay. So here it says Jupiter and the moon. I see the moon here. And where's the Jupiter? Where's it? Over here. You see it here? Okay, I analyze the Jupiter for you. There you are on the top right side, Jupiter. You can actually see Jupiter in the center. On the left, there are 2 moons. On the right, there are 2 moons. Io, Europa, Ganymede, Callisto. Right? So this is taken by where? By Robert Perez from Mexico. All right, I'm an astronomer from Mexico, but I don't know what is this blurry image of the clouds or something here. They didn't explain why he get this. But I feel that this could be a single shot. All right, a single shot. Oh no, not single shot, because you see here the 4 moons very bright. Maybe there's a long exposure. All right, so you see here the moon, the Jupiter with the 4 Galilean moons, Io, Europa, Ganymede, Callisto, all in a single shot. Okay, taken from Cancun. All right, Cancun is a holiday resort in holiday resort in Mexico. Right, Mexico. Now, most Malaysians will say Mexico. Wrong. X is pronounced like H. So the correct way to say is Cancun, Mexico. All right. So we go to the last picture, September the 1st. Very interesting. September the 1st is a video. Okay. Never mind. What saltwater remnants on Ceres. And this is by our NASA. Of course, NASA, this is our Dawn mission. I'll give a bit of information. So NASA, JPL is Jet Propulsion Laboratory, Caltech. All right. And UCA is the University of California, Los Angeles. All right. So this is the Dawn mission. So basically, the Dawn mission is many years ago, NASA launched a rocket that flew by what they call 2 asteroids. One is Vesta, the biggest asteroid, and the second one is Ceres. So this Ceres, but now Ceres has been upgraded. Ceres has been upgraded from asteroid last time to become a dwarf planet. So what they have done is they have detected that a lot of brine means salt water, frozen salt water. So I'm going to play a video now. You can see a lot of frozen salt water on Ceres, all right, by dawn. The pink color one is the brine, is the salt water, frozen salt water. There you are. I play again. Play again. Okay. Now I repeat, that was not a simulation of the salt water. That's a real picture. All right. Remember the dawn was sent by NASA. It orbited around this Vesta asteroid, took a lot of picture, and later on flew closer to Ceres, took a lot of picture. So that's it. And then this is the dawn mission. And remember the dawn mission, all right? The dawn mission uses ion propulsion. Very interesting. It's not the normal rocket, where you have a chemical rocket. You have, say, one is the fuel, one is the oxygen. You fire, you a lot of thrust. The disadvantage of the chemical rocket is that the fuel you cannot carry, you cannot last for a long time. You fire for at the most half an hour, 10 minutes, all gone. But what happens if you want to launch a mission to go to one of the asteroids or go to Pluto? So you use for the dawn mission an ion motor. So ion motor actually is they use the xenon gas, Xe, xenon gas. All right. So when the xenon gas pass through the nozzle, the electrons will strip off from the xenon atom. So now you have a positive ion xenon ion, and this xenon ion will be accelerated by a powerful electric field. And as the xenon goes achieve a fast speed, it will be ejected from the back of the rocket, and you provide a lot of thrust. But because the xenon ion, the number of ions produced not much, so the thrust is minimum. The thrust on the dawn rocket may be just like, imagine a foolscap paper, A4 foolscap paper resting on your hand. What is the weight of the foolscap paper? Very, very little. So that is the thrust of the ion rocket on dawn. But the advantage of the ion motor, you can have the thrust applying for day after day, week after week, month after month, non-stop. The same thrust is given. So the thrust may be like the weight of A4 paper, but you can get the same thrust for week after week, month after month. For the end of half a year, then the velocity attained will be very fast. And that's the advantage of the ion motor. So in future, we hope that more of the rocket missions in the solar system will be using ion motor, right? Ion propulsion, right? I think that's about all. 1st of December. Michael, are you still there?
Yeah, here.
So any question?
No, we don't receive any question.
So all right, too high level. Okay. So thanks again, Michael. Okay.
Okay, sure. Thank you, Dr. Chong, for the
Thank you, Michael.
presentation today. Yeah. Okay, thank you everyone who have been
Okay.
joining us. Okay, we'll see you again next time. Good
See you
night.
again. Bye-bye. Yeah.